Dear students, good morning. In last lecture, we end up with deriving the shape function equation for the four-nodal quadrilateral element. That is, we find out the value for n1, n2, n3, n4, and frame the equation for unknown displacement. That is u and v, as well as find the equation for the we obtain the equation for the x and y. That is n1, x1, n2, x2, and the x3, x4. So next we'll go on to after shape function we'll go move on to the stiffness matrix equation. Now to frame the stiffness matrix equation we require uh, strain displacement relation and stress relationship matrix. So it is the usual procedure. So for any type of element we are trying to frame the uh, shape function equation. After that we are move on to the strain displacement relation, then we are going to move on to the stress strain relationship matrix. So once we derive this, then we'll go for the stiffness matrix equation. So let us discuss with this four node rectangle element. Then this is a parent element and this is the isoparametric element. What we are trying to map, that is what we are trying to do the coordinate transformation here. So here we will see the difference between the coordinates. This is a natural coordinates, this is a global coordinates. And for the natural coordinates, the entire element has been represented in terms of eta and zeta, and here you will have x and y. Similarly, this in this entire that is natural coordinate, the element, that is the coordinate, that is the origin will be located inside the element, but in case of global coordinates, the entire element far away from the axis, that is entire element has been represented using the common axis. So the origin will be away from the element. So there is a major difference. And another thing is nothing but here the magnitude of for the epsilon and eta, that is the eta and zeta values maximum will be 1. But in case of isoparameter, that is global coordinates, it can be depends upon the um, x and y value. So it can be more than 1. That is the major difference between this. So this is the equation what we have seen in last lecture. So now what we are going to do is nothing but now we are trying to um, do that coordinate transformation. Let us say it is a coordinate transformation, or we are going to represent the straight edges element into uh, um, that is isoparametric element. So we are trying to convert the natural coordinates into global coordinates. For that we have to express the entire derivation of a function of x and y coordinates in terms of eta and derivative of epsilon zeta coordinate. That is the main objective is nothing but first we have to convert this eta zeta into x and y. So for that let us take f is a function which depends upon x, and f is a function that depends upon x and y, that is the global coordinates. But whenever the interchanging the global coordinates, it can be that each and every individual x and y will be represented in terms of epsilon and eta, and epsilon, that is eta and zeta, and eta and zeta. That is why I am trying directly related this, why I am not trying x is equal to zeta or y is equal to eta, since we are doing the coordinate transformation here. So we cannot exactly this is it is a coordinate transformation takes place. So exactly we cannot able to locate the eta and zeta uh, position, because we are changing the entire coordinates here. So eta and zeta position also changes. That's why we are representing x also depends on eta and zeta, y also depends on eta and zeta. So let us be clear in this. F is a general function that depends upon x and y. This is what we are going to represent now. That is we are finally obtained that f x and y individually depends upon epsilon and eta, because we are trying to shift the entire coordinate, that is we are trying to convert the entire coordinate eta and zeta value into x and y. So we don't know that is we cannot able to fix exactly x is equal to zeta and y is equal to eta. So that's why x also depends upon epsilon and eta, and y also epsilon eta. So it depends upon epsilon eta. So in order to represent this relation between natural and global coordinates, we introduce the we are going back to the chain rule of partial differentiation. So we'll use the mathematical formulation here. So in order to relate the two coordinate system, that is x and y. So that is here I am representing the eta and zeta in terms of uh, just relating the eta and zeta with respect to x and y. So this is a chain rule for the two coordinates x and epsilon and eta. This is dou f by dou y zeta and dou f by dou eta is equal to dou f by dou x into dou x by dou epsilon plus dou f by dou y into dou y by dou zeta. Similarly, in terms of eta, dou f by dou x into dou x by dou eta plus dou f by dou y into dou y by dou eta. So I just rewrite this equation in terms of matrix form. So and introduce this entire matrix, we'll call it as Jacobi. So Jacobi matrix. So Jacobian matrix. So Jacobian is a person who has introduced these types of matrix. So dou f by dou epsilon, dou f by dou zeta is equal to this term is nothing but Jacobi J and dou f by dou x, dou f by dou y. So this Jacobian matrix again I am simplifying it. Dou x by dou epsilon, and this can be written as in terms of position of row and column. So J11, J12, J21, J22. This can be represented in terms of this can be J1, this is J12, this is J21, and this is J22. So now we know the value of x and y, that is n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Y is equal to n1 y1 plus n2 y2 plus n3 y3 plus n5 4. We already derived. So I just differentiate. We know the x and y. So I just differentiate this x with respect to epsilon and eta, y with respect to epsilon and eta. That is what I am doing here. So J11 is nothing but dou x by dou epsilon. Similarly, J12 dou y by dou epsilon. J21 dou x by dou eta and dou y by dou eta. So I just differentiate this with respect to eta and zeta, this x and y with respect to eta and zeta. So that is what I am getting here. So now we know the value of n1, n2, n3, n4 already. We have framed the quadrilateral element shape function values. We have defined it. So I just substitute this value here. That is this 4 equation. That is n1, n2, n3, n4. Wherever the n1, n2, n3 present, I just substitute the values and differentiate with respect to eta and zeta. So that is what I am done here. So 5.37 represent dou n by dou zeta is equal to, I just differentiate n1 value, that is this, in terms of zeta. Finally I am getting 1 by 4 into minus of 1 minus zeta. So that is what. Similarly till n4 I am doing the same. So again, once we find the value 5.37 to 5.44 values into this equation, that is 5.33 to 5.36. So I just now I obtain the value for this this equation. So that is I just substitute this equation for this J11, J22, J21, J12, J21, J22. I substitute this value in this 5.33 to 5.36. We'll get the J11 value to J22. This is my Jacobi value. So J11 is equal to 1 by 4 into, that is what I am doing it. So J11 into this value. Similarly J22 till J22 we find out. So once from the equation we know that I just rewriting the equation number 5.0 what we started here. So my intention is nothing but framing the, that is we have to represent the eta zeta in terms of x and y. So here we are having eta zeta in terms of, that is x and y in terms of eta zeta. So we required x and y, that is we have to convert into global coordinates. So dou f by dou x. So I just interchange this value here. I just bring this value here and this dou f by dou epsilon. So then we'll get the value of this j can be j inverse changed into j inverse. That is this j is j11, j12, j22, j21. So this I will go for this dou f by dou x, dou f by dou y required. So I just keep it in this side, and this can be go like so. It will be like inverse. So j value is nothing but we'll change it to inverse. So j inverse can be represented 1 by mod j into adjoint of j. So that is what I'm doing. Adjoint of is nothing but this will be interchanged, as well as the sign has been the sign will be negative for this one, or you can go for cofactor values. So dou f by dou x, dou f by dou y will get this one. So my intention is we have to get the dou f by dou x and dou f by dou y. That is what the intention. Finally we have to obtain the isoparametric. So isoparametric has to be represented in terms of global x and y coordinate. So again I'm recording the strain displacement relation for two-dimensional element epsilon x, epsilon y, gamma x, y shear strain is equal to dou u by dou x, dou v by dou y, so on dou u by dou y plus dou v. So we require dou u by dou x and dou v by dou y. So and similarly dou u by dou v plus dou v by dou x. So we have to find this value. So for that what I'm doing is here we are so far deriving in terms of function only. That function can be anything, any field variable. So here the structural problem, the function is nothing but u and v, that is displacement component. So first what I'm trying to do is nothing but I will take this 5.50 and function wherever the function present, I just substitute f instead of f is equal to u. That is use one of my displacement component. I just represent the 5.50 equation. Wherever f will be present, I will just replace with u. Similarly, at same equation, wherever the uh, f present, I will just represent in terms of v. So that is the two displacement component, since it's a two-dimensional element. So I will represent in terms of this efficient generalized function. That function can be field variable. So that field variable can be here for two-dimensional u and v are the field variables. So first same equation I am replacing the u, and so similarly we are replacing the v. So same equation we are replacing v. So then equation 5.151, 5.52, 5.53, 5.51, 5.25, that it's nothing but 5. I just substitute the value of 5.52, 5.53 into 5.51. That is, we require dou u by dou x, dou v by dou y, and that I will get from here. Similarly, we require dou u by dou y plus dou v by dou x. So I just substitute this value in this equation, and then write it in a matrix form. We'll get E is equal to Ex Ey gamma xy is equal to 1 by mod j into this matrix form will give dou u by dou epsilon, dou u by dou eta, dou v by dou epsilon, dou v by dou eta. So this will be a matrix form. So we know that u and v is nothing but n1 u1 plus n2 v2, n3 v3, n4 n4, and v is equal to n1 v1 plus n2 v2 plus n3 v3 n4. Then we require this value dou u by dou epsilon, dou u by dou eta. So we'll go for so dou u by dou epsilon is nothing but, so I just differentiate u and v with respect to eta and zeta. That is what I'm done here. So dou u and u with respect to eta and zeta, v with respect to eta and zeta, I just differentiate this equation. So we know the value of u and v. I just differentiate with respect to eta and zeta here. So once we know that this equation will return this 4 equation has been written in the matrix form. So this matrix form will get like this. So this is the value what we required here. So I just substitute equation 5.55, that is 5.59, into equation 5.6. Sorry, I just substitute the 5.59 into 5.54. I just substitute the 5.59 here, that is the value of this one in the equation here. So instead of this, I substitute this value, right hand side value. So now substitute 5.59 value in the equation 5.5, we get 1 by mod j into j22. This is what this entire thing will call it as b, that is 1 by mod j into this matrix will call it as b, that is the strain displacement relation, and u is nothing but u1 v1 u2 v3 u3 v4. This is the displacement component, or global displacement vector u. So b represent the entire thing. This from mod by mod j into this. Mod j is nothing but Jacobi matrix, determination of Jacobi. This is what we have done here. So again I'm trying to reduce the equation. E is equal to b into u. The entire equation can be represented. v is equal to 1 by mod j into this value. That is what we discussed here. But still we require dou n by dou. So this value we already derived. That is, we know the value of shape function n1, n2, n3, n4. I just differentiate with respect to x and eta, that is epsilon and eta. So we already got this value from the equation 5.37 to 5.44. I just substitute this value of this value, that is dou n1 by dou epsilon, dou n2 by dou epsilon, similarly dou n by dou eta 1, eta 1. So I just substitute this value in terms of eta and zeta. We will get value of this value already we got by this equation. Then if you refer this equation, we'll get this. This is what we get from 5.37 to 5.44. We are already calculated that, we have already derived that value. We just substitute this value directly. So b is equal to 1 by mod j. In terms of eta and zeta, we'll get 1 by 4 will be common. So this strain. So this entire thing is nothing but strain displacement relations. Strain displacement relation is nothing but b represents the strain displacement. So this E is nothing but strain, and B matrix is strain displacement relation, into U is nothing but this is the global displacement vector. So once we know the value of strain displacement relation, we required D matrix for the K matrix. This is the K matrix for the generalized K matrix for the any structure. K is equal to integration of B transpose, cyclic integral of B transpose dB into dV. For isoparametric element, we will represent in terms of global coordinates, that is this dV represent thickness into dx, so this dou x dou y, that is the representation here. So double integral of, we'll go for double integral of, since two-dimensional element is a double integral of dou x dou y into t. If you want to represent in terms of natural coordinates, so natural coordinates will be represent dou x dou y will be converted to mod j into dou epsilon dou eta. The dou epsilon dou eta natural coordinates coordinates, and mod j is nothing but transformation, Jacobian transformation. So this is the importance of Jacobian transformation. Nothing but it is used to convert uh, that is this is used to transfer the natural to the global coordinates. So that is the mediator for that entire mapping or coordinate transformation. So when you go for natural coordinates, for integral will represent -1 to +1, because the entire magnitude of the natural coordinates limit is nothing but 1. So that's why -1 to +1 we are representing here. Double integral b transfer to b, t will be always out, the thickness will be constant, and instead of dou x dou y in some natural coordinates we have mod j into dou epsilon dou y. Whereas this is nothing but dou x dou y. So determination of Jacobian, mod j is Jacobian, b is strain displacement relationship, d is the strain relationship matrix. So d value is nothing but stress strain relationship matrix. So this, since it is an also two-dimensional element, we have already derived the d matrix for the two-dimensional element. Is the common from the Hooke's law. There are two conditions are there for two-dimensional problem. That is one plane stress condition, another is plane strain condition. If the problem will follow the plane stress condition, we'll use the d is equal to e by 1 minus nu square, this matrix value. If it is the plane strain condition problem, then e is equal to 1 plus nu into 1 minus 2 mu into this matrix will use. So these are the two these are the d matrix. So b transpose, once we know the value of b, we can go for b transpose and d, it will give the k matrix. So this is how the k matrix for the three node, k matrix for the 4 nodal quadrilateral element. So this is all about the isoparametric element, that is 4 nodal quadrilateral isoparametric element. So we just have the quick review of what we discussed on us. Left of last lecture with final n1, n2, n3, n4 with respect to x, y, that is geometry of the element as well as displacement component of the element with respect to shape function equation. And then from the shape function we are trying to frame the element stiffness matrix. So for that we have the parent element and isoparametric element, that is eta, zeta and x and y. So for that coordinate transformation we used for coordinates transformation relation, that is natural coordinates and global coordinates relation can be calculated by using chain rule. I applied the chain rule for the epsilon eta and x and y. So based on that, we'll otherwise this is a chain rule. So based on it, we will try to find the equation for this individual uh, strain displacement relation. So once we know the strain displacement relation, we will go for stress strain relationship. So stress strain relationship will be same for any two-dimensional element. With respect to it, it will be represented in terms of Young's modulus and Poisson ratio. That is what we are getting. Once we know the value of d, then we will go for b transpose dv into dv representation. So based on quadrilateral, it will be dou x by dou y. It is isoparametric global coordinates. This is a natural coordinate. Can be represented in terms of dou epsilon dou eta. So that is all about the state function equation, stress strain relationship matrix, and strain displacement relationship matrix, and stiffness matrix for the quadrilateral element. So in next video lecture, we'll discuss about we'll solve the numerical problems related to what we'll discuss in this video. That is what we'll discuss about the stiffness matrix. We will find this, how to find the stiffness value for the 4-noded quadrilateral element, and how to obtain the value of uh, x and y are uv at non-nodal points. That is by using safe function. So we'll solve the problems related to 4-noded quadrilateral element. Thank you.